Hello, I'm Dimitrios Pagonis. I'm an associate professor at the University of West Attica, and I'm going to present our study entitled A Novel Engine Air Intake Sensor based on 3D printing and PCB technology. One of the main objectives was the design and the fabrication of a novel engine air intake sensor, which combines three simple things. First of all, 3D printing technology, additive manufacturing technology that is, with printed circuit board technology, or PCB technology. We will see later what is PCB technology in more detail. Second of all, it employs an airflow shaping housing geometry. CFD simulations were employed in order to design an appropriate housing for this sensor. Thirdly, it addresses the measuring challenges which are present on the intake flow of an IC engine, of an internal combustion engine. We also validated the functionality of this device, of this proposed device, at an appropriate experimental setup, which is an engine testbed. And the key features of this proposed sensor is low cost, robustness, and simplicity of fabrication. As we all know, automotive industry employs a wide range of MAFs. MAF stands for mass airflow sensors, and their role is to maximize the efficiency of the fuel mixture during combustion, during engine operations. The majority of these sensors are thermal flow microsensors, and this is because the research conducted in the last 2 to 3 decades have led to a great reduction in their cost. Now, in this study, we present a novel air intake sensor which is based on an alternative method, and this method is a combination of PCB technology, printed circuit board technology, with additive manufacturing. The proposed method has potentially numerous applications, and these applications are not constrained only in the automotive industry. For example, one interesting application could be in marine engineering, where there is a need for on-site manufacturing of replacement parts. Regarding 3D printing and PCB technology, 3D printing was employed for manufacturing of the sensor housing, and this housing is necessary in order to provide the airflow shaping, which is important since it addresses two issues. First, the measuring challenges on the engine intake, where the most important is the restriction of the backflow induced during an internal combustion engine operation. And second issue to be addressed is the measuring range, which is quite large for an airflow sensor, even for a medium-sized engine. And the solution there is to form an appropriately designed bypass pathway where the air velocity decreases significantly, and locate the sensing elements inside that pathway. Regarding PCB process, printed circuit board technology is a relatively new fabrication process which comes from the combination of printed circuits and MEMS technology. It addresses some basic drawbacks of the standard macroelectronic processes. Relative information can be found in the reference shown in the slide. With regard to the design of the sensor housing, we have some specifications and challenges to be addressed. First of all, a typical airflow of a low power engine is in the range of 0 to 600 kilograms per hour, or 0 to 8,800 standard liter per minute. And we have to take into account also that there is an available PCB-based flow sensor based on author's previous work, and this is what we are employing. It utilizes the hot wire principle of operation, and it has a measuring range from 0 to 180 kilograms per hour, since saturation was observed above that point. Thus, we have to make an appropriate housing to expand this measuring range, this limitation from the previous work, above 180 kg per hour, and this is done by creating a bypass pathway inside the main tube for the flow, and this pathway, its geometry, it has an effect apparently to the resulting flow profile that was estimated through appropriate CFD simulations using the SimScale online platform. The topology of the housing design features 5 main elements. First of all, the main pathway with a corresponding air inlet and air outlet, the internal bypass pathway for the incoming flow, an appropriate orifice at the inlet of the bypass pathway in order for the flow to be reduced inside the pathway of the bypass, the backflow restriction, and the sensing element. Key points for the performed simulations are the following. The assumed maximum engine air intake was equal to 615 kilograms per hour. The resulting air velocity, taking into account the cross-section of the air inlet, is about 32 meters per second, which leads to a Reynolds number inside the bypass pathway equal to 31,382, pointing to turbulent flow. For that reason, SST-K omega turbulence model was employed for the estimation of flow profile, and the resulting geometry exhibits a drastic drop of 84% of the initial flow, resulting to a 5 meter per second air velocity over the sensing area. This drastic drop can be seen more clearly in this figure, where the velocity along the center axis of the bypass pathway is presented. As we can notice, for a 30 meters per second air velocity at the inlet, we obtain about 5 meters per second air velocity over the sensing area. Similarly, in this figure, the air velocity along an axis which is perpendicular to the incoming flow is presented, and we can notice the same reduction as in the previous figure. The obtained final geometry, together with the resulting dimensions, are presented in this figure. For the fabrication of the housing, fused deposition modeling was employed through a typical commercial 3D printer. The sensing element consists of 3 commercially available PT100 RTDs, which are mounted appropriately on a PCB substrate. The developed sensor was initially characterized on a diesel engine testbed, which consists of a low-power industrial engine coupled with an eddy current dynamometer. In this slide, we can see the experimental setup diagram employed. Note that the device under characterization is mounted in series with the integrated MAF that is used as a reference sensor in the setup. Both engine speed and mechanical load applied are controlled accordingly by the testbed control station. For the characterization of the device, hot wire principle of operation constant current was chosen, supplying 40 milliamps to one of the RTDs. The engine air intake was varied by running the engine at various speeds, and that is from 0 to about 1700 RPM, which corresponds to an inflow range from 0 to 260 kilograms per hour. From the figure presented, we can notice a 10% variation of the RTD's initial resistance. From the obtained initial results, we can conclude that the functionality of the prototype device was well demonstrated. According to the obtained results, the housing printed through 3D led to a significant increase of 45% of the measuring range with respect to the author's previous work. The saturation noticed above 260 kilograms per hour was further investigated, and the key points are the following. Air velocity inside the bypass pathway does not exceed 5 meters per second even for maximum inflow. The RTD sensing element has an initial temperature of 118 degrees, which decreases to 79.6 at maximum airflow. On a separate characterization of the sensing element, when it was mounted on an appropriate testing tube, No saturation was present, even at increased flow rates where the temperature was decreased to 52 degrees. From the above remarks, we can safely assume that the sensor signal saturation is not originated due to significant decrease of the sensing element's temperature. Thus, the developed flow profile at the sensing area was further investigated through appropriate CFD simulations. The additional CFD simulations revealed a circulating flow at the end of the bypass pathway for closed well below of 260 kg per hour and in close proximity to the sensing element as shown in the figure. We should note at this point that the sudden expansion at the inlet of the employed bypass can lead to a boundary layer separation with a reattachment point that can be situated near the sensing element. Both of the above geometry-induced effects can potentially contribute to the saturation which is observed at the sensor signal. Regarding further work, we will focus on optimizing the sensor's housing geometry utilizing standard airfoils. In more detail, an optimum bypass pathway design will be developed through appropriate CFD simulations, where the inlet and outlet geometries will be based on standard airfoil geometry, for example NACA airfoils. By shaping appropriately the flow profile at both inlet and outlet ports of the bypass, we should minimize the boundary layer separation and the circulating flow, expanding the sensor measuring range. The fabrication of the optimum housing by 3D printing technology will follow, together with appropriate characterization of the resulting sensor. This concludes our presentation. Thank you for your time and attention.